Good evening, Mrs. Bavel. How's it going? Jabram, welcome aboard. So yeah, we'll get started. We're going to be covering some of this stuff. Um, you got a 3.2K upvotes on R Simulated. That's the way to do it. And the R Simulated folks love, they seem to love these Houdini sims for the most part. Thanks for pointing them my way. Get all the karma. Bad itchy scrote. Maya Unreal Engine 4 user? Yes, these things are pretty VEX heavy, and VEX is a programming language inherent to Houdini or proprietary to Houdini, but it's very similar to like the RenderMan shading language, if you've ever used RSL or that. And then it's also just based loosely off of like C++ in terms of coding structure and stuff like that. There's a lot of things that are different to like a power user between VEX and C++. But if you're familiar with reading C++ code, you'll probably be pretty far ahead of the game when it comes to like reading VEX. All right, so we'll get started. Just get this in the file. Is this the, yeah, this is the 22nd. Week number 6. All right, so we'll make the geometry like this, and we'll get started. So this was the first thing I wanted to talk about. It's just an introduction into what's referred to as matrices, or matrix for computer graphics. So this is the main kind of like new thing we'll be, fuck matrices. This is the main new thing that we're gonna be talking about this week. For the most part, you don't really need to know like low level what's going on with these matrices. I'm just gonna do like a brief overview for people that have just never heard of them or anything like that. But basically, the fundamentals of computer graphics are made or rely on matrices. If you've rendered something, like a matrix is used generally to transform your world space into camera space, which is like scaled for the render. And then if you use like screen space position and stuff like that, all of that stuff is built off of matrices. And then Houdini, the way that it's constructed here, if we do like a test, just get Tommy in the mix, bring out the big boys for this one. When you're moving him around at this level here, or the object transformation, this underlying like technology or inside of Houdini is using a matrix to store the transformation. The reason that they do that is because when you're trying to keep track of like a translation, a rotation, a scale, and then parent it, so in Houdini, we do that with a null. When you start to stack and have all of these like parented, nested transforms, it becomes quite complex, as we've seen with that nested spinning thing we did a while back. To keep track and like manage all of those parenting hierarchies is very difficult. So matrices are a special, very like deep math kind of way of representing and recording that information. It's stored in this kind of format that's like a row column array pretty much. So it's like a spreadsheet, and they generally look like this. This is what's called an identity transformation. So the identity will always have ones diagonally, and it will always be a square. So it will always have as many rows as it has columns. and the diagonal will always be 1, 1, 1, 1, 1. So in Houdini, if you have like a scale, just make this guy, beef him up, pork him up a little bit. And then up here, this is like a rotation. And then up here at this other level, we'll do like another rotation and a translation. So we're stacking a lot of these relationships. In Houdini, these all get kind of what's called concatenated or flattened down into a final matrix. If you really want to look at that matrix or take a look at it, Bad Itchy Scrote, thank you for the tier 2. 3 months. Got all the 3-monthers in here today. So if you want to take a look at it, if you just get a Python shell, I think it's, let me see, world transform. This will return the final matrix that is basically the nested, like flattened relationship of all of them. So you don't really need to know, like pay attention too much as to what's going on with these numbers and what each one is doing, especially for today's course. But just know that it exists like underlying with the technology or whatever to basically stack and flatten all of these transforms into a single data type that's called a matrix. So in the past, we were doing floats, scalars, just like one value. The luminance or black and white, you just need one number for that. We were doing vectors for like a position. This is the XYZ position. So this is a special data type that gets used to record usually scalar translation. Usually scale and rotation, or if it's a 4x4 matrix, it will be used to generally record rotation, scale, and translation. In other cases, these will get used to record other types of data, like it's just a generic array, so people use them for other things, but most commonly in Houdini, they get used like this. So I'm just gonna get rid of this guy. It was just talking about how that stuff gets made. And then I have this linked up here, if you wanna play around with it. The numbers get a bit wonky with Houdini. They do like the floating point precision stuff, but generally you could see like the scale right here is being recorded there. If you want to like do translations and stuff like that, you can start to see how these numbers are modified. It will get quite confusing as you make more and more like transformations or parameters up here, but for the most part, I would say just you don't really need to pay attention or be too worried about like what these numbers are. I would generally, especially for today, I would just think of the matrix as like an arbitrary, like a kind of holder or just a storage format for a transformation. And then this is a special thing that I'm doing from the XForm SOP or the transform SOP, where you can output the operation that it's doing and record it as a matrix like this. It gets set as a detail attribute. So that's basically what the matrix is. Don't be afraid of the matrix. And we'll keep going now. I just want to grab take another one of these. So I have this nomen, the translation handle thing. And then we'll just use a wrangle. We'll use this in the regular points format, and we'll make a identity matrix. So there's a special function in VEX, it's just ident, and it just generates or returns an identity matrix. So it's generally you just use it to initialize it. The identity matrix is basically like no transformations being applied. So the diagonal used to store scale, and it's just a unit scale or a scale of 1, and then there's no rotations or no translations being applied. So it's just a basic kind of empty transform. So if we take the point position, we multiply it by the matrix, nothing happens. But we've applied basically the transformation to the point position. Then this is the general way that you apply a matrix to point positions, is you just multiply. For other things like normals or other special data types, you might do a different operation, but for position coordinates, to apply the matrix, you just multiply it. So if we want to make an actual operation or a translation or something like that, they have all of these functions built in. So there's rotate, scale, and translate. You could see here, these are the same wording or the same names as the transform SOP. So basically, you could recreate or remake the transform SOP this way. The way that these functions work is the first argument is the matrix you want to operate on. These are kind of special functions compared to what we've used before. Like they don't return. You don't say like the matrix equals the result. Is kind of like a void function. You just pass the matrix through it and it will perform the operation on it. So we're doing a rotation, and then the next argument, you usually use the amount. And then this is similar to what we did with the sine function, where this is in radians. So if we just do pi, this would be like a half rotation. And then the last argument people usually use is the axis that you want to rotate around. So we'll just do 1, 0, 0 for x. I'll just get rid of these other ones and we'll just make sure it's working. So we did our rotation. Is ident just setting the defaults, like int variable equals 0? Yes, it's setting the defaults, but the reason why you can't just do 0 is because, might work here, but the reason why people typically don't use 0 is because you want the diagonal to be 1s. Otherwise, if you start a matrix and you manually put zeros in everything, your scale would be set to 0. So this is why people usually use the ident function. It's like a special thing just for matrices. If I did there's some special functions you can use to set like every component of a matrix. You try. I'm not sure, but generally that's why people would use ident, is just to basically say it's a fresh, empty transform. It's the same idea as initializing a variable like that. Oh, I think, so my node was bypassed the whole time. Let's try this again. All right, so that's why it wasn't working. Yeah, if you just set it to 0 or you do nothing like that, it won't get a scale, like a unit scale, and it would be basically initialized to 0 and nothing will show up. Sorry about that. User error. So we've done essentially a 180 degree, or rotated like halfway around a circle, around the x-axis. So if you take the x-axis like that, flipped it, like that. And then you can do a scale. Again, this is using the matrix that we want to scale as the first argument, and then the next argument is just your scale. So this usually gets passed as a vector because you could scale it in each axis. Like you could do an X, Y, and Z scale that would be unique in each axis. So you could do 1.5, 1. You'd see that it's getting half as high. It's getting squished by half in the Y direction. If you remember previously, sometimes we did like the vector function to essentially cast a scalar to a vector. So if we do vector 2, this is saying each component gets twice as big, or each axis is getting scaled by 2. So this is just shorthand of doing this, this, this. They mean the same thing. The reason people do it is because if you just say 2, sometimes this will return an error, or depending on the data type you send it. Like if I say float scale equals 2, and then I try to pass it. It looks like I'm not getting it, but sometimes you'll get a warning. Maybe they've updated this function where it will kind of automatically take care of that for you. But generally, just to be clear, whatever people might cast it to a vector themselves. It looks like we don't need to do that. And then the last one is the translation. So translation is the same thing as like an offset, or just moving the point in 3D space. So we could do set 1, 0, 0. You just go this way to be consistent. Then we've moved it 1 unit in X. So if we wanted to, we could promote all these parameters and make like our own transform SOP, or we've basically just recreated the transform SOP. One other thing to be careful about is like the order of these operations is pretty important. So if we do this, looks like that one, let me try going in a different direction. So if we switch this and then do that operation last, you can see we get a different result. So these instructions are kind of processed in sequential order. So like in 3D space, if you're saying move this many units, then rotate 180 degrees, then scale, you might end up at a different position than if you said like rotate 180 degrees, then move this direction, depending on the order of operations or the order of transforms. You'll end up in different places. So that's why on this node right here at the top, people don't really change these. Like people will usually just make more transform nodes and then do the specific operations in the order they want to. But if you really want to, you could do like rotate, translate, scale in that order. Sometimes people refer to it just as the initials, TRS, TSR, or SRT, and so on. So this essentially is why matrices are so important, because it takes that transform order like out of the equation, or it bakes it in. So if we were thinking about our object level nested transforms that we had, if you want to record a bunch of complex operations of like parenting something that has a scale offset, a rotation, and then a translation, and like as you nest all of those operations, if you want to tell someone else or tell a software package like perform this complex set of parented operations, it would be very difficult to describe it to the software if you're like, do a translate, then a rotation, then a scale, then a translation, then and like in these specific orders and in this like complex chain of commands. So that's essentially the biggest benefit of the matrix. Is you just bake down your final operation into a single data type. So hopefully that makes sense. It's like, don't get too worried about what's going on in the rows and the columns, but just know that they're used to basically, in this sense, concatenate or flatten down a set of complex kind of operations. So I'll just say this is a simple transform using a matrix. So the reason that this gets more powerful with VEX, or the reason you might have to use it, is because you can vary the inputs of this at a per point level and get more interesting results. So if we just get rid of the operations for now and we just go back to a scale, could do, let's keep it this way, but we'll do a rotation around the y-axis. And then something we did in the past was take like the length or the distance of the point from the origin and do an operation based on that. Or even just like, if you remember the bouncing balls example, we just took the x position and then fed that through like a sine wave to get bouncing. So if we look at, let's just set the color to the z position. So we kind of have like a mask or an alpha channel along the z axis. So it's getting 0 right here along the y and the x, but z is getting brighter as it moves along the z axis. So we're just visualizing it right now using the color, but we could use it to drive the transform. Instead of using a constant value of pi, we could just say, use the z position. Then you get some kind of interesting warping happening. So this stuff is happening here because the arrow along x has some thickness and it's just like flipping around itself. But you get some bending or twisting or stuff like that. If you want to really get deep into some of this stuff, one of the interesting challenges or like explorations you would want to do is maybe trying to recreate some of these bend or twist, taper, etc. One of these SOPs and trying to like rebuild it yourself could be a more advanced challenge. Especially if you're interested in like tool building or just like recreating some of the nodes is a good way to practice learning something. If you look inside of this, all of this stuff is built using VEX. You can see they're doing it, building using matrices and doing, there's a lot of code and complicated stuff going on in here. But just to recreate it from like visually looking at the result and figuring out yourself could be an interesting task to do. So if we get our window here, you would see how long it is. Generally, when side effects writes their VEX code, they're more verbose than they need to be, or they just write more lines of code than you generally would as like an artist or a user, because they're basically trying to cover a ton of like edge cases and be more descriptive than they need to be. But if you're working in production, you're generally just trying to produce one like visually interesting result, so you don't need to build out tons of lines of code to handle like different user inputs and stuff like that. You had to do this stuff to get a path deform going? Yeah, that's another thing that they started, they've been building out more and more of these things to make it less, where is it? The path deform. This kind of thing is super useful. Sometimes working with packed geometry or packed RBDs, those will record the transformations. Like if you do a RBD simulation, it will record the rolling and stuff like that in the matrix. And then, of course, if you've ever used or started to look into the kin effects, all of that stuff is the joint transform and stuff is recorded in matrices. So knowing this is super helpful anytime you're trying to go like deeper into the software or the operations. So let's just clean this up a little bit. One thing I'm going to do is just keep playing around with this. So if we go back to our color, we can look at the length of P. So we do that, and that is just the distance from the origin. It's kind of like before I was just taking the distance or the distance along the z-axis. This is an easy way to just say in every direction, how far are we from the origin? We could do that now instead of just doing z. So we do that, and we get a funny little warped space. You can do extra things, multiply it by bigger numbers, do the exponential, the different filtering operations and stuff like that we had done before, and cook up all kinds of wonky spaces and distortions and stuff like that. So we'll do scene share. If you're new to the stream, we have this system set up here to update everyone with the file I'm working on. If you do !hip, there's some instructions there if you want to set up a shelf tool. It would basically let you do like a one-button click, or you could get a list of everything. Just quickly lets you fetch and merge the current like working scene that I'm using. So this week number got enumerated like one number higher, but basically the fetch latest will just grab my nodes and shove them into your current Houdini scene. You can also just download the link manually and open it that way if you want. So if you're interested in going deeper with these kinds of things, another thing that you might want to look into, let me just get this one in. All right. So what I've done here is gotten, this one's a little crazy. What I did here is just take 3 grids for each axis and put them in. I'm just going to clean this up a little bit. So if you were familiar with some of the early like filtering operations and stuff we did, I think if you get I don't know if I have them in here. If you remember from week 1 with the bouncing, I did a ton of different graphs and different examples and stuff like that for kind of different curves you might want to use. So you can plug those in or kind of reuse them here. So like one of them we did was 1 divided by the exponent of a number. We were doing time before, but you can do it based off of the length or the distance from the origin. So if we just look at this compared with that, it's just a different way to do like a fall off or something like that. And of course, you could keep multiplying or scaling the final result. Forgot the operation. You can start to do kind of like bending space or warping space this way, kind of like a black hole or something like that. And right now we've just done translation, but if you were imagining like a black hole or something like that, we would want to also do scaling. So instead of stuff just getting kind of sucked around forever, you could do some kind of pinching of space, or some distortion. We probably want to do the other result. Let me just go this way. So I didn't explain that the best way, but we want to be taking something called the complement for scale. If I could just make a graph to visualize that quickly. This was the kind of stuff I was talking about from week 1, but it's just always a useful thing to do is just make a line, subdivide it, or add more points so you have more resolution. And then with another wrangle, this is basically just like using a graphing calculator or something like that. So if you make a variable, I just call it u because it's like a UV coordinate, or just the distance along the line, and you put the height into it, then you can kind of plot your curve or plot your function that way. So we'll say the x position or the x offset is equal to the same thing. Then we basically have like a y equals x, or just a linear kind of increase or slope. And if we do the y position, we could visualize this function. So instead of the distance from the origin, I'm just going to visualize u in this case. So it's starting at 1 and decreasing as u goes on, or in this case over here, as the world space gets further from the origin. We used it before to do like a decay. So if this was time, over time, the bouncing of our particles or balls would get dampened over time. So we did this over here to make a twist. So very close to the origin, or 0, the twisting is 1, or a really big number. And then as we fall off or get away from the origin, we dampen or do less twisting over 3D space. But if we want to scale this or suck everything in, we don't want to, if we keep a high number or the bigger values near the origin, we'll be expanding that out. Or dampening, like as values get closer to 0, the scale would get pulled in as we get further away. And that wouldn't make as much sense. So what people call is the complement, or it's just a shorthand for saying 1 minus. Whoops. Is just that. So you can see here we have kind of the inverse effect. If you're used to like image manipulation, images are usually in 0 to 1 space. So if you're inverting an image, you're just doing like 1 minus the current pixel value. So that would make black white and white black, and so on. So we could set this up and just copy and paste it like this. You would see we're getting what I was afraid of here. Basically, close to the origin, instead of doing this, we're currently doing this operation. So close to the origin, stuff is remaining at the constant or its input scale. But then the further we get away, things are starting to pull in. So if let's just take out the multiplier. And then if I do 1 minus, then we're starting to get our suction effect. I could do this inside of the parenthesis. And then if we want to do some scale or something to exaggerate the effect, I think we're actually going to have to do a few more complicated math to do that. So you would multiply the distance here, and then we get ahead of myself here. So I think let's just take let me hold off on doing that for right now. But as you can see, before we did this, we had a constant scale, and then we added the scale, and now we're getting some pulling in of the space overall. I think actually the easier way to do that would be to do like a power or an exponent on the result. So this will kind of let you taper or change how much things are getting pulled in and out. If you do something below 1, it would be kind of the opposite of that effect. So this is kind of like how much you want to do your pinching of space. And then lastly, if we wanted to do some translation, we could keep going along the same path, but modulating just the translation closer to the origin or closer to 0. So we probably want to do something similar to this. So we only want to move the point position when it's close to the origin. Like the same idea here, we only wanted to scale when it was close to the origin. We need numbers bigger here, because 0 will basically be nothing. But for scale and translate, I'm sorry, we want to keep similar with this one. Volume warping. Yeah, other people have done, there's different techniques to go about this. You could definitely do this type of effect with what we're doing here. But there's a bunch of different ways to put this stuff together. There's different extra features and capabilities and stuff that you could add in as well. So we want to take the translate, and we just want to do this function. I think it's getting mad at me because I'm just giving it a scalar. So if we wrap everything, RH2, how's it going? This is one of the cases where it gets mad if you don't cast it as a vector. So you can see we're just moving everything in X, Y, and Z further from the origin right now based off of this function that's increasing. But if we want to provided as a vector, we can use the set function. So basically x, we're not doing any offset. With y, we'll do an offset. And then with z, we don't want to do any offset. I think I did too many brackets or parentheses. So now we're starting to do a suction, but it's going up. If we want to go down, you would just do like a negative, like that. So it's a pretty cool method to distort space, kind of based off of the current input or the current coordinates. You can derive like a new distorted, warped 3D space that's really cool for a lot of effects. We'll just keep going. So the next thing I want to do is start with this ocean. Ocean Deformer. So if you guys haven't used this before, this is using some really interesting, like Jerry Tessendorf techniques for generating like really realistic 3D oceans. Originally, this was the Houdini Ocean Toolkit. There was like a C++ plugin you'd have to compile yourself. But over the last like 5 or 10 years or whatever, more and more 3D software packages have kind of built this plugin and included it by default. Like they have Houdini Ocean Toolkit for 3ds Max, for Cinema 4D, and for a bunch of other stuff. But yeah, it has really good, interesting, like very user-friendly controls. So what we could do is remove the directional bias, and then we just kind of have waves that they're not biased or tending towards a certain direction. They're all kind of independently moving around. And then if we combine this with what we were previously doing, you can see we're starting to make this kind of vortex effect, or like a maelstrom or something like that. So in this case, we might want to do more suction. I'm just increasing the amount that we're gonna suck y, or the height down as we get close to the origin. And then we're starting to get something that's pretty cool. So it doesn't really look like things are moving right now. If you want to augment some of these effects, you could start to use some of the stuff we talked about previously. This is a more advanced technique. I don't know how much, try to make it as clear as possible, but we're basically gonna do our operation here using a distorted input position, but not apply it to the final result. So if you guys remember from last week, I think, we were generating noise and using it to distort or to warp the point position around and grow ivy that way. You do that similar thing here. So if we do a noise offset, we'll just keep using the curl X noise. And just generate it based off of the point position. So if we want to apply the noise, we can just add it to P. And that's what we get, is this just curl noise, like wind, kind of blew this stuff around in every direction. If you want to tweak it a little bit, you might want to go with like less amplitude. And then you just have less of the effect. But in this case, we don't want to modify the point position with it. What we want to do is just use this in this during these operations. So basically, we're measuring the length from our noised up position. We want to do the scale kind of varied based off of that noise. And then we also want to do the Y suction based off of the noise. So you can see one way to visualize this or to do it is you could just multiply this by a channel. It would be like a boost. So if I make this parameter, and then you can see what this is doing. This is basically kind of embedding the noise or imprinting the noise into the operation that we're doing. So it's getting a little bit cooler, but it's still not kind of flowing. It's just static. So if we want to do a little bit extra stuff, what we want to do is offset the point position. So if I add an offset to it, set. Right now we haven't done anything, but if we offset Y or the height based off of time, we just boost this up a little bit. Might have been too much. Classic whirlpool. Yeah, so we should, I think I'm going the wrong way. I'm going up instead of down. And let's just increase the amount a little bit. I might want to do adjust the frequency of my noise position. And I think I want this to be a smaller number and a bigger boost. Let's get this. So it's kind of close. I don't know how much time I'm gonna spend tweaking this. You can start to get the idea. Bad itchy scrot. Sorry, I don't have time to answer the question. I'm gonna try to continue to blast through this lecture for right now. Let's try a little bit lower time. Something like that. Or you start to get some pulling of stuff or distortion like that. Another thing you can do is offset the rotation over time. So right now we're just doing a static spin, but if you add time to things, then you start to get some overall rotation. You might want to include this in the mask area. like this masked out area, we're basically just rotating stuff but ignoring the perimeter based off of the distance like this. So if you did, it's just over time, this will spin everything more and more over time. So if you want to do some more exaggerated stretching and stuff like that, you can do some interesting things. So we'll do an update. Get my shelves out here. If you guys want to get caught up. The VDB Deform, yeah, Seller Hassan is asking about showing the VDB Deform setup. So I'm planning to do a stream with the cloud person running, possibly this Wednesday, or the upcoming Wednesday of the next week. But yeah, it's a more advanced thing I didn't want to kind of include it into this VEX series, but it's something that I'll definitely cover in the future. There's using matrices to kind of create a local space noise, but it just didn't fit that well in with this series of workshops. There's a more advanced kind of technique that's like assuming a lot more knowledge, or it's basically like not really intended for people who haven't used matrices before. So that's why I didn't want to include it in this. All right, so we'll keep going and just do something with the classic point generate technique we were using before. What's cooking? We're doing some matrix deformations and stuff like that today. So introducing people who haven't used it before to the matrix VEX data type, and then doing some like warping, rotation, spinning, and translations and stuff like that. So we'll take our point generate. Don't want to do any of these operations yet. So I'll just comment out the area where I'm applying the matrix to the point position. And let's move these point positions around. So if you guys remember, from the first week, if you take P, do the sine and cosine, you can create a circle. So in the x axis, the x component, if we take a sine of the point number, this will just go back and forth in one dimension. If we combine a second dimension, the cosine, then we get a circle. Coming off the mountain bike straight into the VEX is a challenging day. So we just have an evenly spaced sampling of this circle. If you want it to be random, you can just use the random function we've used before. So do this. And, oh dear. All right, let's see if my clipboard works this time. All right, and then we just want to scale these. You do pi, and that's like a half circle. You do 2 pi, and that's the full circle. So now we just have a random sampling of the circle. So it's a little bit more broken up. And then if we want to make some kind of like triggering system or start to move these around, let's just start with the color. So everything's black. Let's make a time, or t. And if we just visualize it like this, they start at 0, or when we have 0 seconds, they're completely black, and then they just get brighter or increase in intensity over time. We could kind of offset this if we wanted to. So if we subtract a random number generated, just want to keep using it based off of the point number. So we just doing this, it generates a random value between 0 and 1 for each incoming point. So Houdini, or every like 3D software, all of the elements of the geometry get unique index numbers, and then we're just generating unique values based off of that. So now if we take a look, everything's lighting up around the circle. Xanders, how's it going? In a sequential fashion, because we've used the same seed for all of our random functions. If you want a new random number, you can just offset this. And then visually it will be more random. Before we were using the same number, so the distance or the position on the circle was the same as the time offset. But now we're using a different number or different random seed for the time offset than we are for the coordinates. So that's pretty cool. It glows. So I want this, instead of going from 0 to whatever time increase this is, I want it starting at 1 and then going to 0 over time. So we can do that using the fit function. This function's really useful because it changes the range, but then it also clamps the final result. So at the end, you can be sure that your numbers are specifically between a range, and you don't have to worry about like things being negative numbers or really big numbers. So right now we're taking maybe 0 and 1, and then we can flip it around and go from 1 to 0. So now over time, things will randomly switch from kind of on to off, or fade from 1 to 0. If you want more of a delay, you can multiply your random number. So now, instead of doing a time offset between 0 and 1, we're doing a time offset between 0 and 2. If you want to go even further, we go up to 5. So everything's going to decrease at the same rate, but it just gets offset as to when it's starting and stopping. The reason I'm being so specific about this is because we can actually use it to modify or scale the point position. So if we do this, instead of just assigning it to the color, now we're just using it as a multiplier. Or it's the same idea as doing a scale operation. And then if we feed this motion through our kind of complex set of operations, let's just only do the rotation. Then you can see we're getting some spinning. You could do this maybe with less So now we have kind of a particle vortex motion or something like that. If we want to bring back the translate, it looks like this one, I'm a little bit too like zoomed in for my point position. So if we just take P here and multiply it by a little bit, and then we can change the scale of our suction. Sometimes you can change this, like if you do a exponent here, you can start to boost. You might want to go the other way. So I'm basically trying to get things that are moving more quickly when it gets closer to the center and slower when it gets when it's at the perimeter or the edge. Let's try going with it bigger. So hopefully you can start to see it. If you look at the trail node, let's see. Let's just leave it how it was, but we'll take the length and divide the increment by the length. So this will normalize your length to always occur like over a single frame. So if you take 24 steps, each step is 1/24 of a frame increment. And then this will just let you visualize like the direction of everything a little bit better. So these should be curving around or basically getting pulled in, like rotating around more and more quickly as they get closer to the origin. If you want to manipulate things a little bit further, one thing we could do is like, here everything's moving towards the origin or towards the center of our circle at a constant speed. We're just multiplying this by the linear function. Again, this is a situation where you can use all the different kind of animation curves, like animation shaping functions we've used before. So like the smooth, this gives you an ease in, ease out kind of effect. You get some more interesting results that way. You can also do a power function, again, to shape some of these results. So this is going to make it really quick and then deaccelerate at the end. And if you do numbers less than 1, this will kind of have the inverse effect. So things are like accelerating to a really high speed. MVP POW. Yeah, for doing any kind of like VEX operations, I usually rely on power somewhere. It's very similar if you've done like color correction or stuff like that to a gamma function. It basically gives you some more like dynamic range in your numbers. So instead of just linear increases that in an animator's sense is just always like a very boring like static movement, the power function gives you more like sporadic, interesting kind of results. So you could even do maybe t divided by 2. And let's bring back our... So now we have a more interesting kind of black hole effect. And I think we could play around with this spaghettification. So yeah, I think this power, I wanted to go the other way a little bit. So yeah, that's the idea with that one. Let's do this as maybe a particle black hole suction. I think this one. Just set it to 5 because it looked like it was dipping the edges a little bit without it. Yeah, you can reverse it to make it an hourglass. So if you were familiar with some of the other weeks we've done with the balls, we did some reflections to get things going the other, bouncing off the other direction, like mirroring 3D space using the absolute value function. So we can do the same thing here. Like if you just do p dot y equals the absolute value of p dot y. What we've basically done here is reflect things across the origin. So anything that's negative becomes positive, anything that's positive becomes negative. If we want to do this to a subset of our points, we can do that using the if statement. So we can generate a random number. We want to offset it again to make it unique from all the other random calls we've done. And then if we just check if that's above or below 0.5, so this is giving us numbers between 0 and 1. If we check if it's above or below 0.5, we're basically saying for half of the points, do this reflection or this operation. So we have kind of the inception dreidel thing happening right now. But if you want to also do your offset, you can just use the Egyptian brackets, so the curly brackets, and then that will let us do more than one command for the if statement. So we can take the y position and offset it. I think I went too far. It's all the way down there. So probably want to do 2. No brackets required. Yeah, that's kind of a shortcut or a hack. If you want less typing or stuff like that, you can omit the curly brackets, but as you can see here, if we completely eliminate them, then this next command is getting applied to everything. It's like with the VEX coding, it's not white space sensitive, so it doesn't really care about the indentation of stuff. This is just to be like human readable or whatever, but if you don't have curly brackets, it will just follow the immediate next command and then keep going. So yeah, and then if you want like a bit of an overlap or something like that, you can get something a little bit more interesting. So I don't know what you would call this, maybe we'll just call it the hourglass. Yeah, and then Swash was mentioning the spaghettification. So that's like a terminology for like the dimensional warping, right? So again, if we take this code that we were running, just kind of like viewing the distortion of the coordinate system, but we can run that through just a character. So sometimes for these operations, you'll need to subdivide space a little bit, or subdivide your model so that as it gets deformed, it can basically it has more edges, more geometry to play around with, or like modify or deform. So we have the genie, it's kind of doing some kind of warping, teleportation effect. You can use these modifiers or these deformers. The grains version. Yeah, you can even use these in pops. They have the pop wrangle, or you use it in dynamics with them. We'd see this way, basically, as he shifts in 3D space. We're feeding him into this operation, or he'll follow these guidelines. So even if I template that, he'll follow that curve. So yeah, this is the spaghettification, where his limbs, or you basically your body gets like stretched or whatever to infinity, or however long you're going. Wikipedia has a great illustration. Wikipedia has some really good like demonstration GIFs and stuff like that I've seen before. Some of them even they'll render it in like POV ray or stuff, and you can actually look at like the source code for their if it's like a CG GIF that someone was nice enough to generate, like you can actually see the math behind it, which is pretty cool. So yeah, this is one thing you can do. If we take maybe even an animation. So this guy walks and then hits the thing. If we just offset him, so he'll end up at the middle. We could get rid of the hammer, so maybe it just looks like he's going to be screaming, writhing in pain. And then the way that they set up this animation is that these are packed geometries. So if we try to do our operation here, the packed geometries will get treated like rigid transforms, like you can't deform it because it's just a single point that's representing the geometry. So if you guys are familiar with packed geometry, it's kind of like instancing inside of Houdini. And basically, each of these pieces, having a hard time getting them to display it. Let's go into the bigger font. So instead of each point on the mesh being a unique position, it's parented under a single transform. So when we apply our code to it, it will get treated like a rigid piece. Rigid just means kind of non-deforming, like only one operation gets applied to it, which is the position offset. So if you're trying to do like a rigid body thing, you can do interesting like cracking and destruction operations with this. But if you want to allow him to deform, you can just do a convert node, and that will basically unpack it and dereference it or put it into unique geometry. And it looks this way because it's the normals don't get reoriented with the code. If you want to, you can tell it to update the normals, or you can also just like discard the normals. And then that way they'll automatically just get recalculated by the viewport. So maybe this, I don't know if this animation isn't really perfectly synced up to things, but with some, the unpack node will work as well. The convert node is a little bit brute force. So Arch2 is saying, what if you use the unpack node instead? Unpack will convert the geometry, but sometimes it will give you polygon soups if you have, or also if you have multiple levels of packing, it will just unpack one iteration by default. So convert is like a brute force method to basically say like fully dereference this and just go to actual polygons. Sometimes with this you'll unpack it and get polygon soups or some other stuff like that. But yeah, both will generally work. So you might want to do more scaling. Try offsetting him more. Oof. The actual difference between polygon and polygon soups is a little bit beyond this this workshop, but it's basically just like I've used it here for the ocean surface. It's just a slightly more optimized way of representing like large data sets or large sets of topology. So it just uses one polygon to represent all of your mesh. So it discards like a lot of extra operations you might want to do. Like if you want to set a unique color to each of these faces, you can't do it to a polygon soup. It's more efficient to render these and to do other operations or like store the geometry. It will take less space, but it's one. So it's like a kind of trick or whatever that they're doing, like behind the scenes, they're ignoring a lot of information that typically is used. Like there's better reading and stuff you can do, I think, on the polycount forums. Someone might have gone through it. I think it's used for games and other stuff like that. But it's basically just a special data type that's maybe Houdini has the best. There's a Wikipedia entry for it. They're basically saying that it's unorganized polygons, or like they're just ignoring a lot of the connectivity and other information that like typically gets like baked into stuff. So for really heavy data sets, it's a little bit more optimized. You can use them, like in Houdini, sometimes people use them as a bit of a trick or whatever. So if you have one poly soup, you could have like each island of geometry as its own poly soup. And then like when you're generating random numbers, they get unique for each island, or there's a bunch of different reasons people use polygon soups. But the main reason it was invented and incorporated into Houdini was to be a more optimized method for storing and rendering really big meshes. So if we just take a look at this as polygon soup, again, if you want to get rid of the polygon soup, you can just do the convert node, and then you're back to all of these polygons. So you'd see here, this is taking up 20 megabytes of memory. And then without this, it's just down to 13 megabytes of memory. So especially if you're doing GPU rendering where you don't want to fill up your VRAM as quickly, that would be a situation where you would want to use a poly soup. certain modeling operations, you can't run them on polysoups, like the poly extrude, for example. If you wanted this to have thickness, like a diorama style or something like that, nothing happens. It's kind of, doesn't even tell you really, but it just won't be able to operate on the polysoup. If you convert it, then it will be able to perform its operation. In this case, you probably don't want to extrude like along the normals. You just want to do a global transform in the height direction. So you have less editing capabilities. You have less flexibility when things are polysoups. It's more of like a storage and rendering format. So that's generally like how I think of it. Even for the viewport to visualize this, it would be a little bit slower to be working with polysoups. Might not be that easy to see with this many. If I go up to like a 1K grid. I might need to display the FPS and stuff like that, but you get the idea. It's just a more optimized format and stuff like that. So yeah, I think with this guy, if we wanted to accentuate the effect, just making him smaller would be the better way to do it. You could also add some controls and stuff like that to like expand the effect out or things like that. But yeah, this is the spaghettification, the stretching. So if you've ever seen the, like Swash was saying, the astronaut falling into a black hole, it's this kind of visualization where his arms get really, really spaghetti noodled out. So yeah, this is pretty much it that I had planned for today. If anyone has any questions, you could feel free to drop them in.